to build our own custom machine learning algorithm for predicting crop yields from the given data. This is a project for the competition from Venusmoon, so congratulations for them. And in this project, we have been given a training data and a testing data with years, crop types, rainfall, soil type, and irrigation area. We have to predict the crop yields. So we have to utilize all the given data for predicting the crop yields. And let's move on to some exploratory data analysis. Now we can see some kernel density estimations for the numerical columns. We can also separate them based on the crop types. We can also see a histogram of the patterns of the data. As you can see, most of the time the mean and median value of the given numerical data are completely almost aligned with each other, and there are no visible outliers. And you can see we can also separate them based on the crop type that shows a different patterns, and we can see the categorical variable of the data crop types are also equally divided, so it's good for us. And we can also see some data on loamy and alluvial soils separated as well. But as you can see, the data is perfectly divided among the soil type, so we don't have to consider the soil type for in our data, because if we consider rice, we know that it is cultivated on alluvial soil, so we don't need any separate columns for soil type as well. And we can see the patterns between the given year and the crop yield as well. We can also see a patterns on them. That way we can predict the missing crop yield for the given year. That's a general trend of the crop yield based on the given time series information. You can see a correlation between rainfall and crop yield. The maximum correlation is observed between irrigation area and crop yield. That's a 98% correlation. We can use that information as well for accurate prediction. As you can see, there are a lot of trends, visible trends that are available on the pair plot. But as you can see, these trends are that's how the way the data is arranged. It's not an actual trend, but the actual trend is the relation irrigation area and crop yields. As you can see, we can see a lot of a linear relationship between the two. We can utilize them, and now we have to verify if the crop yield is dependent on irrigation area and rainfall. We can use a hypothesis testing. For that, we can use a Pearson correlation coefficient for that, and we can verify that the irrigation area is impacting the crop yield, but the rainfall is not impacting the crop yield. That's an interesting information that is available for us due to the hypothesis testing. And now let's see the relationship between the year and crop yields. So they are almost a linear relationship is available on them, and if we can see, we can even do it better. We can fit a polynomial function of higher degree, and the more we increase the degree, the more better we can see the results. That way we can also see a polynomial relationship between irrigation area and crop yield. And moving closely, we can see there is a relationship can be observed once we increase the polynomial order. That way we can use them use these curve for accurately predict the missing values, and we can even get better results for the irrigation area once we fit the a polynomial curve of higher degree inside them. Even if we can ignore the confidence intervals and uh, extract the perfect uh, curve data of the from the given polynomial equation. And now we can split the data into xy and further divide them into training and testing split. Can also define a function for visualizing the cross validation. And now we are ready to build our custom regressor using the base estimator and regressor mixing base models, base classes, and we can use the above given trends and using the polyfit function from NumPy to build our own model which fits the a polynomial curve of higher degree to the given data, and we can predict by using the polyval function as well. So that's we can also extract the equation of the curve using the equation. Um, that's how our cross-validation visualization works. As you can see, the 52,000, the mean square error is available on the for our model. Now let's compare with other models. From linear models, we can try linear regression, which is getting a lot higher mean square error compared to a model. We can also try ridge regression, lasso regression as well. On the decision trees, we can try decision tree regressor, add a boost regressor, extra tree regressor as well. For gradient boosting models, we can use cat boot regressor, and in ensemble we can try a random forest and bagging regressor as well. And now let's compare our model accuracy with other models. As you can see, compared to the all other machine learning models, our model is performing better, way better than other models as well. And compared to all other models, our model is performing way better. So that's interesting thing for us to uh, remember. And we can also extract the equation of the curve so that our model can be expressed uh, in a explainable way. And now we can look at the business recommendations. These recommendations are extracted from the exploratory data analysis, the trend we have observed so far. The farmers can use crop selection and rotation and things like that, and the farmer has to um, assess the risk of all the other factors that are missing in our data, like floods, pests, and all the unfortunate things that can happen in the agriculture. And there are a lot of factors beyond that farmers has to consider that. Then the farmers can use our model for even better prediction. We have also uh, used these uh, models, and we have deployed our model in our website as well. So, but finally, we conclude that our machine learning model is performing well, way better compared to the most of the model, because most of the times the machine learning models are only approximating the target variables from the given data, instead of just trying to solve the problem head on. So, thank you so much, and thank you for the opportunity.